All right, let's get started. So on Monday, you will have your midterm, so just a reminder of that. I think a good way to study would be, so you get to bring in an 8.5 by 11 piece of paper with notes on both sides. So, maybe like consolidating the main ideas that we've covered in the class and deciding what you want to write on your sheet and making your sheet is like a good starting point for where to study. And then I think looking at the problems in Galleon and especially the review exercises that come, there's like a set of extra exercises after chapters 1 through 4, and then I think again after like 5 through 8 or something like that. Those are all good questions to look at. So just like picking out practice problems from there. Did you have a question? Yeah.
Which was the last lecture?
So it's going to cover chapters 1 through 7. So the last one, let me just open up my schedule. So it doesn't cover external direct product whenever we did that. So the last lecture it covers is the one from March 6th, the orbit stabilizer theorem. Yeah. Okay, other questions? Okay, so let's get started then. So today is the last lecture about groups. So next Wednesday, we'll start talking about the next main object of study of this course, which is something called rings. And today we're going to finish off groups with two very important theorems. So the first one is going to be called something called the first isomorphism theorem, and then we will also cover something called the fundamental theorem of finite abelian groups. So let's get started. So last time we talked about homomorphisms. So these are maps between groups that preserve the operation. So with phi of AB equal to phi of A times phi of B when A and B are elements of G. So let's state the first isomorphism theorem. So last time we saw that the kernel, so all of the things that are sent to the identity in G prime, we saw that that is normal in G. So the kernel of phi, which is a subgroup of G, is normal. So we could look at the corresponding factor group and wonder what is G mod the kernel of phi. And the first isomorphism theorem tells you what that is. So it says, so we're going to let phi from G to G prime be a homomorphism. Then we have the following. So G mod the kernel of phi is isomorphic to phi of G. So what is phi of G? This is just phi applied to all elements of G. So this may not equal all of G prime, but it will be a subgroup of G prime. And we can say what the isomorphism is. So this is with the isomorphism defined by sending a coset G times the kernel of phi. This gets sent to phi of G. Okay, so this is the first isomorphism theorem. So let's prove this. So for the proof, we're going to need to do several things. So we will prove that these two things are isomorphic using this isomorphism. So the first thing that we'll need to do is show that this map is well defined. Let's call this psi. So we have to show that psi is well defined. We have to show that it's injective, surjective, and operation preserving. Okay, so I'm going to give you a few minutes to think about how to prove this, and then we will go over the proof together. Okay, let's go ahead and prove this. So to show that it's well defined, we need to show that if A kernel phi is equal to B kernel phi, then phi of A is equal to phi of B. Okay, because that's where these two elements get sent. And this is true by something that we proved last time. So I think it was like the first theorem, property 5, so I'll scroll back a little bit. Yes, so we had this, this property, so that exactly tells us that this map that we've made is well defined. Okay, and then why is it injective? So that property was an if and only if, so we also have the reverse direction. So if phi of A is equal to phi of B, then A kernel phi is equal to B kernel phi. So these are both by 5 in a theorem from last time. Okay, so then surjective is more or less automatic. So say we have an element phi of little g, so this is a generic element of phi of big G, then the coset G kernel phi, this is an element of G mod kernel phi that gets sent to it. Okay, so so far nothing has been too difficult. We've done most of the work for these previous parts. We've done this in the past. So now let's check that this is operation preserving. So I'm going to apply my map psi to two elements of G mod kernel phi. So I'm going to do psi A kernel phi times B kernel phi. Okay, and we want to show that this is equal to psi applied to each of these separately and then multiplied, right? So we want to show that it's equal to this. Okay, so I think this is pretty straightforward in that at each step you just do the thing that you know you can do. So for example, I think in this expression, the only manipulation we know how to do is we know how to multiply these two things. So let's go ahead and do that. So we get psi AB kernel phi. Okay, and then now we know how to apply psi to a left coset, and that just gives me phi of whatever this thing is. So this is equal to phi of AB. And then since phi is a homomorphism, it preserves the operation. So we have phi of A times phi of B. Okay, now what is phi of A in terms of psi? This is psi of A kernel phi. And what is phi of B? That is psi of B kernel phi. Okay, so this calculation tells us that psi is operation preserving, and so that finishes the proof that psi is an isomorphism. So that is the first isomorphism theorem. Yeah.
I'm still, is that the first step shows operation presumably, like to get A and B together, I believe,
So this step, yeah. So this is by definition of the group operation in the factor group G mod kernel phi. So like to multiply two cosets, you just multiply the corresponding coset representatives. Yeah. Other questions? Yeah.
For surjectivity, why are we not assuming just kind of like arbitrary element of G prime? Why are we assuming an element from B over G?
Yeah, okay, so we're showing that these two things are isomorphic, right? So my isomorphism needs to be surjective onto this thing, not onto all of G prime. Yeah. Other questions? Okay, so let's do just a quick example to see what this theorem is saying. So and this should come as no surprise. So let's consider the map from the integers to the integers mod n, where we take an element, let's say a, and that gets sent to a mod n. Okay, so I think we've talked about last time that this is a homomorphism. And the kernel is equal to numbers that are divisible by n. So you can think of this as the subgroup generated by n inside of Z. So by the first isomorphism theorem, that tells us that Z mod this kernel is isomorphic to its image, and this map will be surjective, so that gives me all of Z mod n. Okay, are there questions with this example? All right, let's see another theorem. So we've seen that kernels are normal subgroups. So we may ask, are all normal subgroups kernels? And we'll see that in the next theorem that the answer to this is yes. So we'll see, given a normal subgroup, how to define a map, a homomorphism for which it is the kernel. So let's see how this goes. Okay, so let's let n be a normal subgroup of G. Then n is the kernel. Hold on, let me write it this way. So n is equal to kernel of phi, where phi is the map from G to G mod n, given by sending a little element, or an element little g in big G to the element, the coset Gn. Okay, so what do we need to do to prove this theorem? Well, I think possibly it's not clear that this map is a homomorphism, so we'll have to prove that phi is a homomorphism. And then the second thing that this theorem is claiming is that N, our normal subgroup, is the kernel of this. So we need to show also that the kernel of phi is equal to the normal subgroup N. Okay, so I'm going to give you, again, a few minutes to think about how to prove this, and then we will go over the proof. Hey, where you been? What you need? Okay, let's prove the theorem. So to show that it's a homomorphism, all we need to do is show that it's operation preserving. So we'll compute phi of AB. So this is equal to the coset corresponding to AB. So this is AB times N. And then by the way the group operation is defined in G mod N, this is equal to AN times BN. And then individually, these are each equal to phi of A and phi of B. Okay, so this tells us that phi does indeed preserve the group operation, and so it is a homomorphism. Okay, so now let's see why the kernel of phi is equal to n. So let's let G be an element of kernel phi. Well, G is in kernel of phi. This implies that, so when I apply phi to G, that I get the identity in G mod n, which is equal to n. But what is phi of G? This is Gn. And then by coset properties, we have that Gn is equal to n, implies that G is an element of n. Okay, so that proves like one inclusion, that proves this one. And to get the other inclusion, basically we can just reverse this process because all of these arrows reverse. So if G is an element of n, then that implies that n is equal to Gn. And since Gn is phi of G, that means then that G has to be in the kernel of phi. So for the other direction, we just reverse all of the arrows. Okay, so then that finishes the proof of this theorem. Are there questions about this proof? Okay, so now I'm going to change topics a little bit and tell you the fundamental theorem of finite abelian groups. So this will tell you, given an integer n, how do we find all of the finite abelian groups of order n up to isomorphism? So this theorem will tell us how to do that. So I'll just write down the theorem, and then we can talk about what it says. So it says that every finite abelian group is isomorphic to one of the form so Z mod a prime number, so this cyclic group, to the n1 power, direct sum with other cyclic groups that look like that. So okay, so I'll comment that the primes appearing below, so I'll say where the P1 up to PK are prime numbers. Okay, the primes appearing need not be distinct from one another, so we've seen that, for example, when n is equal to 2, we have Z2 direct sum Z2 and Z4, right? So these are each of the form listed, and they're different from each other. Okay, so the theorem says a little bit more. It also says that the terms appearing in the product are unique, or in other words, that groups of this form are not isomorphic to each other. So So the sets of P sub I, so this representation, are unique. So obviously up to possibly reordering the terms, that would give you isomorphic groups, but if you have different P's and different N's, then that will give you distinct groups. Okay, so if I give you a group G, let's say G is a finite abelian group. Finding the group ZP1, N1, direct sum up to ZPK, NK, for which G is isomorphic to this group. So this problem is called determining the isomorphism class of G. Okay, so the proof of this theorem is pretty involved, so we are not going to cover it in class, but you do have everything that you need to understand the proof of the theorem now. So if you want to read it, it is done in full detail in chapter 11. So if you would like, you can read that. But let's do some examples. So I'll start by showing you. So we'll compute or determine all isomorphism classes of abelian groups of order 8. Okay, so 8 is equal to 2 cubed. So basically we need to figure out all of the ways to possibly break up 2 cubed into some number of cyclic groups. So for example, we could just leave this as one cyclic group. We could have z to the 2 cubed. But another option would be to leave 2 powers of 2 in one cyclic group and move 2 over to another one. And then there's one more possibility in this case, so we could also fully break this up into a direct sum of 3 cyclic groups. Okay, so these are all of the options for what an abelian group of order 8 can look like. Yeah, question?
If we have like an abelian group G of a circle, is there only one of these options that is going to be isomorphic?
Yeah. And so the way that you can find it is to just start computing the orders of elements. So like, let's say, so what would happen in this case? So say I give you an abelian group 8 and it's presented to you as like a subgroup of a U group or something like that. So it's not really obvious which of these ones it is. You could just start computing orders of elements. If you find that all of the elements have order 2, then you have to be in this one, right? Because this is going to have an element of order 8 and this is going to have at least one of order 4. If you find an element of order 8, you know that you have to be this group. And if neither of those is satisfied, then you have to be this one. Yeah. Yeah, question? For n equals 2, we only have z2. I think for n equals 4, we have those two options. Oh, sorry, I think I mixed up what n is here. So in this one, it was like the exponent. And in this one, I was talking about n as the order. So yeah, sorry for that confusion. Is that clear up? Yeah. So these are groups of order 4. Okay, so I'm going to give you a minute to think about 2 examples. So the first one is to determine isomorphism classes of abelian groups of order. So the first one will be p to the 4th, where p is a prime. And then the second one will be p cubed q r squared, where p, q, and r are distinct primes. Okay, so I'll give you a few minutes to think about this. And then I have like a little demonstration to show you. Okay, so as you were doing this example, this first one, you probably noticed that the isomorphism classes of abelian groups will correspond to ways of writing 4 as a sum of smaller numbers, right? So we have 4, we have 3 plus 1, we have 2 plus 2, we have 2 plus 1 plus 1, and then we also have 1 plus 1 plus 1 plus 1. And each of these will give you an abelian group. So for example, this one would be z p to the 2 plus z p plus z p. Okay, so these this idea has a name. So these are called partitions. So a partition of a number n, and let's say this is a positive integer, is a way of writing n as the sum of smaller positive integers. Okay, so we just saw for n equals 4, all of the partitions of 4. So we have these 5 options. And we have a partition function, so the partition function P of n tells you the number of partitions of n. So for example, for various values of n, what is P of n? So for 1, there's only one way to write 1 as a sum of smaller numbers. For 2, we have 2 and 1 plus 1, so P of n would be 2. For 3, we have, so we saw it earlier in the lecture, we have 3, 2 plus 1, and 1 plus 1 plus 1. So we have 3 options. For 4, we just computed that there were 5. I wrote down a couple of other values. So for 5, there's 7 options, and for 6, there's 11. And you could go on, continue on computing these numbers. So some interesting things about the partition function. There's no known closed form expression. So there's no known closed form formula for this. But 2 things we do have, so there are recurrence relations for computing it. And if you're interested, this is kind of a fun problem to just sit down and think about how to write down the recurrence relations for the partition function. And we also have an asymptotic approximation, which is supposed to be pretty accurate. Okay, so, I lost the... Okay, so let's say we want to determine how many abelian groups are there up to isomorphism of order p1 to the n1 times up to pk to the nk. Okay, so in the second exercise that you all just did, you would have seen that you first need to select a partition of 3, and then you need to select a partition of 1, and then you need to select a partition of 2, and you can pick any of those options. So it would just be the product of the partition numbers of the exponents. So P3, P1, P2. Like that would tell you the number of these. So this is given by, so we would take P of N1 and multiplied up to P of NK. Okay, so I'll give you guys a minute to finish writing, but I plotted for various values of n how many finite abelian groups there are of that order, just using this calculation. So I'll show that to you. I'm going to unplug this. Okay, so here's how I did it. Let's zoom in. Window, zoom. Does anyone see how I might make this bigger? This. Okay. Wow, now it's very large. Okay, so here's how I did this. So this is a program called Mathematica that does it's good for math computation stuff. So it has a built-in command that tells you the partitions of a number. So here's the 5 partitions of 4, and you can see the syntax. It just gives them to you as a list. So this corresponds to the partition 3 plus 1. And it can also factor numbers. So, and this is what that looks like. So 20 is 2 squared times 5 to the first. Okay, so then I define the partition function just by computing. So we want this to be the number of partitions, so it's just the length of this list. And then we want to compute the number of abelian groups of a given order. So we just saw that this was the product of the p's of the exponents. So we're taking the product as I goes from 1 to the number of primes in the prime factorization, and then we're taking the partition number of the exponent of that prime. Okay, so here's a table with the number of finite abelian groups for various n from 1 to 10. And this is maybe not that surprising once you see it, that a lot of them there's only one option, but then for 8 you have 3 because 8 is 2 cubed. So what's controlling when there's a lot? It's when you have a high exponent. So powers of 2 are the winners in this in terms of having a lot of abelian groups. So I plotted it for a lot of values. And now maybe this is too big. Hold on. We go down to 200%. So here's for n from 1 to 200, how many abelian groups are there for that n? And yeah, that's it. So we will have the midterm on Monday, and then we'll start talking about rings after that. And I have office hours right now